does in our day-to-day language. Today we're going to look at work and how it relates to energy. And really, it should kind of make sense. When we do work, when we move objects, we're really changing the energy of that object, and it really takes energy to do work, and it should make sense. We need energy to do work. And that work that we do will go into an energy of the object that we're moving. Energy comes in different forms. There's kinetic or potential energy, among others. Kinetic and potential energy are the ones that are really concerned with mechanical energy, and that's something that we're really focusing on today. So kinetic energy is really energy of motion. So when things are moving, we talk about their kinetic energy. Potential energy is the energy of position or condition, so the potential to do work. So let's take a look at our Newton's second law, which we know already, force is mass times acceleration. One of our big 5 formulas, kinematics, right here is listed, and work. And we're going to kind of combine work, force, and energy through kinematics. So they all have a relationship. All of these topics that we've talked about are all related, and now we're going to kind of connect kinematics, force, and work with energy. So if we use this big 5 formula and kind of rearrange it, I get this formula right here. So it's final velocity squared minus initial velocity on the other side. Dividing both sides by 2 ends up with this formula. And then, of course, this A here, the acceleration on the left side, well, I can use my Newton's second law and say, well, acceleration is really equal to force divided by mass, which is true. It comes directly from the second law. And then I can replace that acceleration with force over mass. And then I can multiply everything by mass. Why not? I'm allowed. I can multiply everything by mass. And then, of course, I would have to distribute it. On the left side, mass will get canceled out. So on the left side, I'll end up with force times displacement. And on the right side, I'll end up with mass in each one of the terms. Now on the left side, you notice force times displacement. Well, that's really equal to work, right? Force times displacement is equal to work. So really, I can say, well, look at this. There's a new equation for work, and it involves this initial and final velocity. So work is connected to this idea of velocity being speed, and that is really what kinetic energy is. This is our kinetic energy. So that by definition, kinetic energy is associated with the state of motion. So the velocity of an object, and of course its mass. So the larger the mass, the larger its kinetic energy. The higher the velocity, the higher its kinetic energy. And change in kinetic energy is really what the work done is. And this is known as the work energy theorem. So the formula that we just came up with, total work is equal to 1/2 mv squared minus 1/2 mvi squared, is really our change in kinetic energy, and it's really our work done. So this here is really final velocity, but again, I'm really not going to put an F there because the other velocity is identified as initial. So the second velocity, just for clarity purposes, can only have the V with it, and it's understood to be the final velocity. So if we can measure the change in kinetic energy of an object, we can actually measure the work that we've done, okay? So if we have this one formula or one question here, we can actually apply the work energy theorem to solve for the final speed, which is what the question asks for. So if I use my work is equal to 1/2 mv squared minus 1/2 mvi squared, and of course work is really, we just said, or we've been saying it for a bit now, it's really force times displacement. I mean, the formula here gives us the force, it's 5 newtons. It tells us the distance, 0.5 meters. It gives us the mass, 165 grams. Now make sure that you convert that to kilograms, because that's what the formula requires us to do. It asks us for final velocity, right? It asks us for the final speed. So that's the big question mark, but it gives us the initial velocity because we're starting at rest. So it is equal to 0 meters per second squared. So knowing the force, the displacement, the mass, and the initial velocity, all of these will allow us to solve for final velocity through algebra. I will leave it up to you to find out what the final velocity is for this particular problem. Please do send me an email or respond to this video and let me know if you have any questions. Now, if we talk about potential energy, so that's the other energy that we discussed here, it's really energy that's relative to the forces in the universe. And the particular force that we're really talking about when we talk about potential energy is the gravitational force. Gravity can do a lot of work in, of course, the y direction, up and down direction, on objects. And because of gravity, objects can possess this potential energy, or energy that is able to do work, the energy that is stored. So if I put a ball on top of a shelf, work is done to lift it. So when I do work, I'm actually transferring energy to this ball. And as soon as I let it go, as soon as I remove the shelf, the ball will fall to the ground. The work that originally went into the ball to put it up on the shelf will now reappear as kinetic energy, and the ball will start to move. So the ball will have a certain amount of potential energy at the top. It'll have zero kinetic energy at the top because it's not moving. But as soon as it starts to move, the kinetic energy will increase and its potential energy will start to decrease. Okay? So really, what is this idea of potential energy? So it's stored energy, and it's available for later use. It's really the gravitational potential energy, because it really is energy that is based on the forces an object is experiencing, and those forces are really the gravitational force in this context. So the gravitational potential energy equals the work required to lift an object to a given height. So the work required to lift an object to a given height, and that work will really be dependent on the force of gravity, because that is what we have to overcome in order to lift it. Plus, of course, the height. How much height do we need to lift this object up? So really, the potential energy formula is mass times the gravity, the force due to gravity, which is 9.8 on Earth, times the height, and that is really what potential energy is. So, in summary, potential energy is a stored type of energy, could be used to do work. The type of potential energy we're really focused on is the gravitational potential energy, which comes from the fact that gravity does exist. Yes, it does. If you hold a basketball like this, this budding baller here up, that basketball has some potential energy in it. And if you let it go, gravity will exert a force on this basketball and allow it to then fall down, move the basketball to the ground, and the basketball will lose this potential energy as it starts to fall. The potential energy will turn into kinetic energy as the object is falling. Potential energy is also known as energy of position, and the higher the object is, so if this basketball was up here, it would have more potential energy than this one, and the one underneath it. So really, again, the potential energy formula is mass times acceleration due to gravity times the height of the object, and that is the potential energy that we are concerning ourselves with in this course. So mechanical energy is really the sum of both kinetic and potential energies in this system of movement. So energy will change when we do work on an object, and how energy this changes really depends on the system. There are two types of systems, non-conservative and conservative. Non-conservative system means that a system can lose energy, and we really can't keep track of it. Conservative system doesn't lose energy. So in a conservative system, and a system is something that we define ourselves. It's a subset of the universe that we're really focusing on in order to solve our problems. This energy in our conservative system can change from one form to another, so it can change from potential energy into kinetic energy, but we do not lose it. The fact that we don't lose it means that we can actually calculate it. And if we know that we've lost maybe 10 joules of potential energy, well, we know that, hey, those 10 joules must have transformed into kinetic energy because we're not losing anything in our system. So we can really keep track of it. So our formula that we're going to be using is mechanical energy is really the sum of potential energy and kinetic energy in a particular system, and we're assuming that our system is conservative, therefore no energy is lost to the surroundings, so we can in fact calculate the energy changes and track them during different parts of the trip or of the object's movement. So object may possess potential energy, kinetic energy, or a bit of both. Okay, and we're always going to be relative to a specific reference point, and generally the reference point is the ground when we're on Earth. So that's considered to be height of 0. So in this example here, we've got 3 or 4 different points on this toboggan, and a person will start at point A, we'll move down to B, C, and then finally D. We do use ground as a reference point, and we can calculate the potential energy at position A. That's what the first question asks. What is the potential energy at position A? So the potential energy formula that we just uncovered was mass times acceleration due to gravity times height. Mass is 42 kilograms. Acceleration due to gravity is 9.8 meters per second squared, and then the height is 16 meters. So all we have to do is really just multiply these 3 together to come up with our number, and that will be, just going to use my calculator quick. So we've got 42 times 9.8 times 16, and that's going to end up being 6585. And I'm going to keep all of my significant digits. This is in newtons. I really should have only 2 significant digits, right? Because that's what I've got in these questions here. I've got 42 kilograms. This is 3 significant digits here, but I've got 42 kilograms for mass. So I'm going to keep it to 2 significant digits, and that really is 6,600 newtons. All right, so that's really what we should be rounding this to. But for my future calculations, I'm going to use this other result, because that is the result that will allow me to continue on and get more accurate next step. So the second question is, the person has potential energy of 45 joules at position B. How high above the ground is he? So, well, if the original height was 6585, this new height is 45. So we have lost about 2,085 joules of potential energy. But we know that he's got at position B, we know the potential energy. So potential energy, again, if we use the formula, potential energy is equal to mgh. We've got 4,500 joules. At that height, mass has not changed, g has not changed, then we can easily figure out the height. So we're going to do 45 divided by whatever 42 times 9.8 is. And that's 411.6. So that ends up being 10.9. So height is really 10.9. And we're going to round that to 11 meters to keep it in line with our 2 significant digits. So that's 11 meters. The first one was 66 joules. And let's move on to our next problem, which is the person loses 49. So now we know how many joules of energy we are losing when he moves from A to C. How high is the person at C? Well, if we started off at A with 66 joules of energy, and then we lose 4,900. So let's go 66 minus 4,900. I'm going to be left with 17 joules at C. So at C, PE, potential energy, is really 1,700 joules. And I got that by subtracting 6,600 by 4,900. And now that I know what the potential energy is at that point, I can easily calculate the height using my formula. And again, the mass is 42. The potential energy we just said is 1,700. The G is 9.8. So again, we can figure out the height. And 4.2 times 9.8 is still equal to 411.6. So 411.6, and that's going to be equal to 4. So height is really 4 meters here. So height is 4 meters. It's really 4.1 meters. I guess if I want to keep, actually, I should keep with my 2 significant digits. So let's go ahead and write it as 4.1 meters. What is the potential energy at level D? And this one does not require us to do any calculations, because we can figure out the height at level D, and that is the ground. So level D is the ground, and the height at ground is 0. Because the height is 0, potential energy is also 0. Joules. That's it for this question. Hope you're getting a hang of it. let's go on to talk about a little more about mechanical energy. So we actually do mechanical energy to do work every single day. So we talked about it briefly. We said kinetic energy, potential energy add up to give us mechanical energy. It's not the only type of energy in the universe. Oh my goodness, there's so many other types. All of them do involve either kinetic or potential energy or both. But there's so many different types. Oh my goodness, are you ready? Chemical energy, elastic energy, nuclear, mechanical, what we talked about, thermal, sound, electrical, gravitational, and light or radial energy. Oh my goodness, so many. Different types have different names, and we can convert from one to another. So oftentimes that's what really happens. Like if you think about photosynthesis, I'll talk about it in a few minutes, we're really converting from one form to another through various different processes, okay? So we're allowed to transform from one form into another. There are two types here, mechanical energy. We both have potential and kinetic in this mechanical energy, and it's really energy possessed by objects that are primarily affected by the force of gravity and frictional forces. So something like a plane flying, or a basketball flying up in air, or a soccer ball, or anything moving. It's really mechanical energy. Gravitational energy really only possesses potential energy, energy that's possessed by objects that are affected by the force of gravity. It is really applied to all objects of the universe. Light energy, also called radiant or electromagnetic radiation, possesses both potential and kinetic. It is energy possessed by oscillating electric and magnetic fields. So oscillating just means moving back and forth in specific patterns. And the application here, wow, do you not love this? This is the aurora borealis, I believe it's called. So those are really the electromagnetic radiation at its finest. Electrical energy can be split up into static and static electricity, and then also current electricity. Static electricity really just has potential energy, and it's the energy possessed by accumulating static charges. I know you've been there, you've all been there. I know I've been there, and I'll probably be there as well in the wintertime when my hair stands up. Electrical energy, current electricity, is really possessed by flowing charges. We are going to talk more about this later in the course. Thermal energy, we're going to talk about thermal energy more in the course as well. It's heat energy. It's not really correct, but it's called heat energy as well. Thermal energy is really fire, randomly moving atoms and molecules. And again, talking about this later on, next unit. Sound energy, possessed by large groups of oscillating atoms and molecules. If you sing, you're going to be oscillating atoms and molecules in the air, and that is what creates sound. Nuclear energy, possessed by protons and neutrons. More on this later. There's a nuclear reactor right here. Elastic energy in a rubber band, really, rubber band. Energy possessed by materials that can be stretched, like rubber band. Chemical energy, energy associated with bonds in molecules. And bonds in molecules really are you know, all about food and sugar and so on. And we're going to cover this in chemistry. So I'm not going to talk about it here at all. Just let you know that it is potential energy, and it is in food, chemical energy. So energy transformations, we can really convert energy from one form into another. So all of those different types can be converted. So energy can go from one form into another. A beautiful example is photosynthesis. Photosynthesis uses energy from the sun, and that's the radiant or light energy from the sun, and converts it to chemical energy in sugar. And this is super important. It's not very efficient, as we're going to see in the next lesson, but it's super important. It allows us life on Earth, because sugar is something that we eat and get energy from it. So the kinetic energy is now then gained, or this chemical energy can be transformed into kinetic energy of animals that eat sugar, including us. And then we can then do work in the environment. So thank you, photosynthesis and all this conversion of energy. Technology is allowing us to really convert energy from one form into another. A light bulb here may not be as efficient as we'd like, but it transforms electric energy into light energy. And of course, thermal energy, not so good. Internal combustion engine, that's in your car, transforms chemical energy in gasoline. Gasoline is nothing more than a bunch of carbon molecules like sugar. And it converts it into kinetic energy of moving cars, train, buses, and so on. So lots of energy transformations going on. Now, the unfortunate reality is that a lot of thermal energy is produced and emitted into the environment. So the question really is, how much energy is there? Will we eventually run out? And scientists are really kind of ponder this, they have concluded that when one form of energy is reduced, the quantity of another form increases by the same amount, which really takes us to this law of conservation of energy. Energy transformations, total amount of energy does not change. So whatever transformation occurs, the total amount of energy does not change. So even though it may seem like I'm losing energy, I'm actually gaining energy in another type. So the total amount of energy has not changed overall, and that is the law of conservation of energy. Total amount of energy in the universe is conserved. Energy cannot be created nor destroyed. It can only change from one form into another. Super huge law that we need to remember. So if I look at a camera here, 1.1 kilogram camera, it slips out of a photographer's hand while he's taking a photo. Camera falls 1.4 meters to the ground. What is the camera's gravitational potential energy relative to the ground when it is in photographer's hands? The answer is 15 joules, but how do we get there? How do we figure that out? So potential energy, we said, well, that's just really mass times force due to gravity times height. Potential energy is influenced by mass, and in here we've got 1.1 kilograms. G is 9.8. We're on Earth taking photos, and it's 1.4 meters above the ground. So this here should give us the potential energy of this camera that's chilling in the hand of a photographer. So 1.1 times 9.8 times 1.4 gives us 15.092, but we got to stick to our 15, our two significant digits, so we've got 15 joules. That's awesome. What is the camera's kinetic energy at the instant it hits the ground? So now all of that potential energy, so the camera is now 1.4 meters, originally 1.4 meters above the ground. And it has we said, 15 joules of potential energy. It has 0 joules of kinetic energy because it's not moving. As it falls to the ground, the kinetic energy increases because, of course, the camera is gaining speed. As it hits the ground, it's actually going to have, the moment it strikes the ground, the height is going to be 0. Because the height is 0, the potential energy will also be 0. Therefore, the entire potential energy will be 0. And that means that the kinetic energy, all of that potential energy, has now been transformed into kinetic energy. So the kinetic energy is 15 joules as it hits the ground. Then the next question is, what is the camera's speed when it hits the ground? Well, now we can actually use that, use the knowledge that, hey, well, I know that the kinetic energy is really equal to 15 joules when I hit the ground, and I know that the kinetic energy formula is 1/2 m mass, which is 1.1 times velocity squared, and then we can figure out velocity here, right? So we can go ahead and figure out velocity using this formula, and we should get 5.2 meters per second. So multiply 1/2 by 1.1, bring it over to the other side through division, and then take a square root. I'm going to let you do that. And in the next lesson, we are going to talk about efficiency, and we're going to learn that most things in life are actually not that efficient.